Wait, I think there's something wrong with my laptop's voice rather than James's, because when this guy said recording on progress, that didn't come out loud to me. Okay, I don't know what the problem is. You have my, you can hear my voice, right? Just to check. Okay, good. Good. So let's now define what functors are. So I'm just going to copy a bunch of things, but we can discuss this stuff. Did I open the namespace? Yes. So let's close this namespace as well, so that link doesn't contain all the time. Okay, so here's the structure. So remember when we defined categories, we defined them from pre-categories. So pre-categories had like all the structure of categories, but they did not have the axioms of unitality and associativity. So the same way we are going to first define pre-functors. So pre-functors are essentially a pre-functor. It's two function. There is this object part, and then there's morphism part. So you see the object part goes from type C, because C is type, to type D, right? Moreover, for any X and Y object of C, if you have a morphism from X to Y, then you get a morphism from like F of X. So this is object is like generic name for F here, right? From F of X to F of Y. Does that make sense, or shall we reflect on this a little further? But so you have two functions, object, OBG, and more. So these are different than like objects and morphisms of categories, right? Because really what happens is like, when I check something here, when I check like opt, what do I get? Yeah, it says unknown identifier, right? So let me actually make this one. But exactly. Okay. So this is like, let's write it down. The object part of the object function, rather. And then there is a morphism function. I'm going to copy this. Sorry. Sorry, yeah. It's, this is the morphism function. Well, we haven't said yet that this F preserves composition, right? Because that's not, composition is not part of a structure of pre-category. Or sorry, I mean, composition is, but I mean, we could have actually at this point said that it preserves composition, but that would be functor. So you know what I mean? Like I'm going to do it in 2 steps, essentially. So let's do some dummy like tests of these things that this definition actually works. So this is going to be some test. So let me actually write this section. We can give a name to this section, test and test. Okay, so I fixed 2 variables, like C is a type which has a pre-category structure. So this guy plus this. So C plus that structure would be a pre-category. And D plus that structure is pre-category D. And now I have F, which is a pre-functor from C to D, right? I guess I could have written this as C. Well, I haven't introduced the notation yet, sorry. So this is a pre-functor from C to D, and therefore it has 2 functions, F0 and F1, right? So this is our F0. You see, it goes from type C to type D. So what it does is like, what this function does is like deleting all these arrows and going, just sending these points to these points, because that would be type C and type D. Forget all about the structure. Doesn't see morphism, doesn't see composition, just sends point to points. This guy, on the other hand, sends morphism to morphism, right? So you can imagine that it deletes the point, but it keeps the morphism, right? But the points are somehow implicit in the data of the morphism, because morphism goes from somewhere to somewhere as a domain and code. So you can really never delete points when you have morphism. That's why actually in category theory, there's a philosophical principle which is we care about morphisms, not objects. Okay? And you should think of morphism as like transformation. I mean, the word morphism comes from Greek word morph, and morph means transformation. Right? So category theory, you don't. So in type theory, you care about the state. These are like a state of like a machine, right? So it's like or room temperature, or a state of any physical system. But in category theory, what we primarily care is about like transformations of these states or like processes, right? So morphisms are primary. Okay. And functors, what they do is like they sort of like, okay, if you imagine it as a physical system, right? Like this is a state A, this is a morphism that makes state A state B. So think of this as like state A is like the current temperature of this, and then I click this button and like 5 degrees higher, and then this would be a state of temperature of the room where it's like 5 degrees hotter, and morphism would be pressing that button. So if I press like 5 degrees and then 2 degrees higher or 3 degrees lower, it would be like composing this would be equal to just putting 3 degrees higher. So these are like very abstract things with modern many systems like category. People do this kind of thing. But a functor would be like, okay, I'm in this room with all this morphism that's like pressing buttons of this, right? And this is a different category. Let's say this is another room but on Mars, right? So it would be like, that room also has some temperature and stuff, right? The different temperature. But maybe there's a copy of this system there. So if I press like, it goes 5 degrees higher here, right? If I map it, it goes also 5 degrees higher, but maybe they start from different starting temperatures. So like the rooms are not comparable, the people in them are not comparable, they're very different, right? But morphisms are the same thing because you do the same action, which is like heating the room. Okay? That's what we care about in category theory. Okay, so when I write X, Y, Z here, right? I declare them to be like where? Where are X, Y, Z? Where do they come from? Oh, here. So they come from C. So when I compose them, FOG, because F is really after G, then I get something from X to Z, right? And now when I apply F dot more G, what should I get? What does Lin tell me? Maybe James, you can participate in this. Where are you, James? Okay, here. Do you know what the result of this would be?
Hello, can you hear me?
Can you type it?
Oh. Hello? I have to.
Wait, I'm not getting how. Okay, how do you know? How do I get maybe here? The top bar is up here. This second. Okay, so chats. Okay, I already clicked on this, so
I don't remember what prefunctor is, but it will just pull out the like.
I literally do not hear anything you say because the voice is so low. So if you want to communicate with me, you have to type. That's the only way right now. But yeah, sorry for this. Okay, so everybody agrees that this is correct. The result of this. Do you understand what Lin is outputting? Yeah. Or not everybody seems convinced completely. So that's this, yeah. So it says the type of prefunctor dot more of G is whatever this piece. Yeah, I mean, this is not perfect in terms of, I mean, what I guess we can ignore is like, we can ignore D because we know that the results are in the category D, right? What we should really care about is this prefunctor dot opt X, which means really the result of applying F to X. So that's like this bit is just F of X. In our informal notation, this is just F of X, or rather F0 of X. That's why there's dot opt, right? And this is F0 of Y. And when I apply F to morphism G, which is like F1 of G, so this is saying really F sub 1 of G goes from F sub 0 of X to F sub 0 of Y. Okay. So, I mean, I didn't spend much time to actually make the notation nice. So the notation is not optimal right now, but if you want, you can actually do it now. I mean, introduce some notations, you know, like maybe 0 and 1 instead of dot opt. Now we can do this, right? You can just, maybe if I have time, I go home and I go to my office and I do this. But anyway, that's not so important right now. And now if I apply F more to GOF, or rather FOG, because GOF would not type check, what do I get? Yeah. I don't know, but no. Okay. You have to press the space harder. I don't know. Okay, so it says essentially the same thing, but now Y is replaced by Z. Okay. Good. So this small test sort of section, which is hidden from the rest of the file somehow, or rather it's not hidden, but it's not intervening with the rest of the file. That sort of proves that our definition was right. I mean, this is doing what we wanted. So usually when you define something, you should do this test to make sure it's doing what you want to do, right? So because sometimes you define something which Lin doesn't complain, so it's correct, but it's not doing what you want to do, right? So in computer science, this is known as problem of specification. You go and work for some software company, and they give like some like trader company or whatever, algorithmic trading. I know this because I worked there for 6 months in the Netherlands. So they come to you and like some people who are brokers, you know, and the market makers, they come and tell you like, I want this tool to automate this part of like, you know, trading. And like some people write code, and it's correct, like it compiles and no error, but it's not what the person who asked you to do, it's not doing that. It's doing half of that, or it's not. So that's also in mathematics. So sometimes you can define certain things, but it's not what it should be. And I think we had some problem before when we were defining, like, remember, like we had image factorization of a function. And at some point we did not put some field. Like we said, image factorization is just a left morphism and a right morphism, but we forgot to put that they compose to the original morphism. So everything was fine. Lin was not complaining, but that was problem of a specification. It was not up to our informal idea of things. So it's good to do this testing here, right? So they tell you like, okay, now we are ready to define functor. We just need to add 2 more axioms, which is preserving unit and composition. Okay, so it extends prefunctor essentially with these 2 axioms. Right? So this structure of writing this, it's like writing, extending semigroups to monoids. Remember, you had the same structure. You have one operation, which is multiplication, but you added like 3 axioms, right? There's associative, left unital, and right unital. So this is that format. It's just more syntax. So maybe I make a comment here. We extend the definition of prefunctor by 2 axioms. So what are these 2 axioms? First, preserving composition, which means compositions in C, MCC, both. And I'm going to copy this and change all compositions to identities. Okay. Now we are ready because we have the structure. We can introduce our notation. We're going to do that. This is usual stuff. Okay. And you see, again, we have these primes for axioms because I'm going to restate these field axioms as like lemmas with like simp attributes. So this is the same kind of thing we did before. I'm going to just copy all of this. Okay, so I just restated axioms. I said, okay, give simplification to them as well. And now I'm declaring some categories C, D, E. By the way, this curly E is very similar to curly C. So be careful of that. If you have problems in reading this, you can change your font. So for example, one thing that you can do, which is criminal almost, is like using this funny font, which is, what is it? It's the Comic Sans. Actually, it doesn't look that bad when you do link with Comic Sans. So you can go to like Ctrl+Shift+P setting, open UI setting, and then there's Comic Sans. You want to see that, or? So there's, you can search for font here. Okay, here's the priority of my font. So the first thing is Menlo, but I can put Comic Sans before that. So Comic Sans actually is not part of that. Like usually, like in your VS Code, you have to write it. I put it here. Okay. Not too bad, right? I mean, it's horrible. It's something. Okay, let's go back. Not a good experiment. You don't see this? Yeah, but you can see more in like arrows and stuff like here. I think it changed back already because I put, yeah, okay. Okay, you can try on your computer, whatever you like. Okay, so I want to do some example first. No, this, yeah, this is C, this is E. If you zoom enough, you can see this. Yeah, I mean, I typed this with MC, not MCC, but so MC stands for, does anybody know? Math, something. It's cal for calligraphy and math for, it's a font. Okay. I mean, you can use different things. Yeah. Absolutely, yeah. Sure. MC. That's nicer somehow. Let's choose this. But F used for functor. So, what about Ooh. Yes. That's so close to MCB. Yeah, B is not bad. Let's keep B, no? Okay. B is like very close to D. Okay, anyway. So I want to say that if I have a functor, I want to prove that identities goes to identities. So how do I do this? Begin and end, I guess. Maybe we have now a lemma for this, right? It's this one. So maybe I want. Oh yeah, same should work because it's. So that's a test that this works. So it has that this works. Great. Now I want to say a test for composition as well. Like, unfortunately, the file that I have written has different notation for composition, but we can change it. Okay. So let's change all this. MCC, MCD. Then I have 3 objects in C. I have a morphism from X to Y, I have morphism from Y to G. And now this is like diagrammatic composition, but I have to change it to G or this O is harder. Wait, what am I doing wrong? Okay. Indeed, I think you should just press it harder. So now G is from Y to Z, which means f of G is from f of Y to f of Z, right? And f of S from f of X to f of Y. So the only way I can compose it is first f of f dot more of what? G, I think, right? No, but G to f, like compose it, right? So if, I mean, this works, but for more clarity, you can put brackets here. If that's option. So any ideas for the proof? Let's also think if everything is right. So this is a test that's not this one, but rather, what is the name here that I have to say? More comp? Did I call it? Yep, compound. Okay, prime, there's a prime. Sorry? That's right. So, yeah. Okay, let's prove another lemma. I mean, to just fill up all these things. So first you tell me what this says while I'm fixing these things. Oh, what is this? Yeah. So I think what's going on here is like, this is composition of functors, right? So let's see. Because you see, I said functors are like morphisms between categories, right? But we should be able to compose morphisms if they are really morphisms. So let's forget these for a moment and just like focus on the idea of composition of functors. So I have like 3 categories, maybe here, C, D, and D. I go to C. Now, I have one functor F and one functor G, and I want to compose this. So I mean, so you see, this is problematic if I write it in D, because there is no category here yet. So I need some other notation. Maybe if you would be able to do it. I don't know whether I can, but let's see. But let's say I want to compose G and F, right? What sort of functor is it? So because I want to make it into a functor, it should be 2 functions, right? A function object and a function morphism. does it do on object? Any idea? Right. So because f is a functor, I have a function f0 from object of C to object of B. And also I have a function from object of B to object of B. These are literally good functions, like honest functions. So I can just compose them, right? So this would be like pair of functions. I mean, not really pair, but I'm using the formal notation. So it would be G0 composed with F0, which means if I have X, I apply F0 to it first, to the F, and then apply G, I send it to G. Now, what about morphisms? So if I have a morphism from X to Y, what do I do? Well, I mean, because F acts on morphisms, there will be something here from F of X to F of Y. And because G acts on morphisms in D, there will be a morphism from G of F of X to G of F of Y. But lo and behold, this is G of F of X. And this is G of F of Y. So I managed to establish a morphism. Right, indeed. So that's how I would define it, right? I would define this to be GF. Now I would define G of F of X to be GF. But so far, this is a default. Right? It's not a function. We did not prove that G of F, this good, preserves the identities and composition. That you have to do. So let's see why that is true. Right? Let's see why first it preserves identity. Okay, if I have identity here, G or F of identity, by this definition, because I'm just putting identity for F. So if we put identity for this, you get G of identity equal to G applied to F of identity. But F of identity is what? Yes, so this is identity of X, and this would be identity of Y. No, identity of Y. This is identity of X, but this would be G of identity of something. That's right. And then this would be, which is still there's one more step further, this is identity of G over F. So G over F of identity is identity of G over F. And that's unitarity. And with the same kind of argument, you can prove like composition. In fact, in the same number of steps. Okay. So let's prove this, right? I mean, well, okay. So I have to go as one step. I was too fast in making this. Forget about this lemma because this already requires this notion of composition of functors. So a lot of steps have to be done here to do this. Let me see. Yeah, and first we have to look for a good notation for this. I'm not so completely sure. And then also we have to, like, now that we are defining composition of like functors, we also have to define identity functor essentially. So we have to do a few things. So let me first define identity functor. Okay. How would you define it? We don't need this particular for not. It's not that important. So it has two parts, right? So this would be ID as an identity function. So it's lambda x dot x essentially. And this would be ID also. Would it work? This doesn't work. Because it says for any x and y, you have to give me an identity function, right? Like if you look at what more was here, the field more. More is not just from object x to object x. It's for any x and y. If you have a morphism from x, y, then you can map it to like object of x to object of y. So therefore I have to say, okay, some lambda, right? Lambda, let's say x, and then lambda y. And maybe if I put this limbically, yeah, okay. It says now the goal is if I have a morphism from x to y, then I get a morphism from identity x to y. Okay, then I guess one more lambda. And now just f. Essentially what should I do then? Well, because this identity, you know what this identity is? This is small ID. That small ID is identity function. It's this one, right? It goes from type C to type C. So Lin knows that that's X. So you just copy. So IDX is essentially ID. Okay. It's not appearing anymore, but okay. Okay, here. That's so weird. Okay, here. Right? So IDX is X and IDY is Y. So you just copy it there. Let's give a notation to this guy. I'm going to give just one. Okay. Why is it one? Because later we will have a category of categories and functors, right? So a category whose objects are categories, that's crazy, right? If you think about it, this is so crazy. You should be really like steam should come out of your mind. Because a category itself can be like category of all types, right? Or category of all groups. And now what I'm saying is like now you make a category of all such categories. Imagine how many groups there are, like all groups of symmetries of objects.
Okay.
And now imagine how many categories there are, because there's so many structures in the world, right? And now I make a category of all such categories. So anyway, that category will have an identity functor. And that identity functor will be the identity morphism of that category. So it makes sense to use the same notation. Sorry, what's the question? Check this one. Oh yeah. Okay. Let's see up there. Can you have category of category? Well. This doesn't make sense. You know why? You see, because category of categories is already a category. So it's like, and then you come back to the first level. So it's not iterative. It's idempotent somehow. That's a very good question. We don't get to that paradox because categories are not sets. So when we say we have category of categories, the second category lives in a different, larger universe. So these are like hierarchy of classes. So I actually avoided talking about this, but this, you've seen the U and V here, right? These guys, they care of this, not getting this paradox. Because as you can see, if I have a type C, right? The category structures on this, and this was true for not just pre-functor, but also categories. Categories of C would live in a type of higher universe because there's this max guy goes to higher universe. So it's like, the problem with sets of all sets is like sets are here, then classes are there, classes are like one type larger, right? So if these are all sets, there is no set of all sets, but there's a class of all sets. So it will be in here. And once you make this jump, then the paradox goes away. Okay. And then there is a second hierarchy of classes of all classes. So the loop has been changed to, has been straightened. And that's the function of universes. We can discuss about it, like this is quite a discussion of its own, but we can talk about this after the class. Okay, so I want to introduce some simple lemmas, just so that we use it later. So this lemma says identity on objects. This is what we discussed, but we have to also teach it to Lean, basically. So I want to say that, what is ID object? I haven't defined it, right? I call it, wait. We still have problem. I have ID. I mean, this is ID and this is dot opt, so that should make sense. That's a definition. Doesn't use what? This one? I'm not sure. Okay. Yeah, why? So forget about this one because that's not fixed, but this should. Would this work? No. Okay, maybe this one also is problematic. Of course, it should be bold one, I think. Okay, I don't know. I will fix it later, so it's not that important right now. To have symptom, we can rewrite, of course. You're right. We wrote it SP1, but I mean it was SP1. I think there is something. So the problem is what is it like? I don't think it's the REFL problem. Exactly. Let's see what the error. So what does it say? Invalid. Yeah, this error, which is usually not so helpful. I mean, there's some problem with type checking stuff going on. That's all I can tell right now. But okay, so it's not that crucial that this works. But let's go back to composition of functors and like actually define like composition of functors. So I want to define like first. So I will fix this and put it later, but for now, let's. So how should I start doing this? Oh, do we have E now? No. Let me go back to change. Yeah, but I mean, my problem with B is like alphabetical, like order, like C, D, then go back to E is a bit of like, weird move. But so how should I start defining this? I want to establish a functor from C to E as a composition of two functors. So it has to have how many fields? 2, right? So one is opt. So let's define this first. Maybe. One is more, right? Okay. Uh-huh. Yeah, it's like the board. Well, G-comp F, actually, that might make sense. Would this work? No. That wouldn't work. You know why? I mean, because G and F are not morphisms. We did with normal comp, didn't work either. G dot up. Okay, that works. That works. What about the map? So this is like G0 composed with F0 that we did on the board. Okay, underscore to see the goal. Okay. So the goal is now is I want something from applying GO. This is like GOF of X essentially, GOF of X to GOF of Y. That's right, lambda. Oh, and then there must be some little space. That's right. So G more of F more of F, right? Some space in between. Yeah, it should be all right. Okay. So okay, great. We could compose functors. Let's give it notation for this. So remember how we actually did notation for categories? I forgot already, so I'm going to copy it. This was the way, right? Because I want to do it like opposite of diagrammatic order. Right now, for example, we gave first F and then G, right? So if I write notation as comp FG, that would be diagrammatic because F comes and then G. But I want to like switch it. And then the way to switch it is like this hack, essentially. So let's do this hack. And now we need, let's hope that O triple O works. No. Okay, we need, what about this? Okay. Do you have a better suggestion? I mean, it's okay. We can also do this for functors, but then there will be real Fs. So we can do maybe sub F. No. C. C for categories. I'd rather do a not let because it's I'd rather be generic and not scope. There is always a chance risk that there will be some C or something, you know. Prime is good. Prime is good. It's better than, yeah, prime is good. So okay, so therefore it's not pre-category composition structure, but actually what comp? Which namespace are we in? Functor comp? Okay. And then I would change this F and G so that it doesn't matter really because these are arguments, but better. This one. So those are precedences, which means like, okay, I don't want to explain this, but like I will explain it on Zulip chat because I will put a link to. It's not really mathematical, so I have other things to do, but like right now, but I will put a link on Zulip chat how to work so for yourself. So let's see. Okay, so I want to prove some basic lemmas and then move to define a little bit more complicated categories, and then we continue later with like defining functors between those categories, right? Because we actually have not done. So what are the categories we have done so far? What are the categories we proved they are categories? Types, pointed. Did we do pointed types? I think we did that last time. No?
I was going to say, I don't remember if we moved to lecture 7.
No, lecture 17 is fake. That's empty in there. So I have to change the order of these things. This will be 17. Okay. No pointer types. Did we do pointer types? Okay. But you do remember types, right? Okay, good. Good. So I believe types were here, right? And for pointer types, it's already in the lecture, but let me explain. So to prove like something is a category, you have to provide like hom, ID, comp, and then 3 axioms, right? So here it is. So I'm saying like this guy, what is the hom type between any 2 objects in pointer types? So here, this X is a pointer type, which means it's a type plus a point in it, right? So really, X is like A with a point in it, okay? And Y is really B with a point in it, right? So if I want to consider a morphism between these things, I just borrow from something we did before. Remember this guy? Right, it says already in the pointer type morphism. So this is from lecture 9 or whatever, 10 maybe. So you can click on it. You can click here, and this is lecture 11, type classes. We did a whole lecture on pointer types. If you don't remember, so this is, go back and review this stuff. But essentially, a morphism between these guys was like, okay, 2 things, right? A function from the underlying types, which sends point of A to point of B. Okay. And then we had a way to compose these guys, right? Here's compose of pointer types. So I'm using all that in here, right? I'm saying, okay, the hom is going to be, well, the hom between X and Y. So these are all like pointed functions from X to Y. And identity morphism is going to be identity of pointer types. So if you have like, so an identity morphism from, let's say, A to, I should use identity hom to AA. So this is informal notation. It doesn't make sense if you write paired AA, because pointer types are different, defined as a structures. But this is really so you know how to define this, right? So the underlying function would be identity from A to A, and because identity sends A to A, it's pointed function. And okay, so I borrowed the composition, and composition was defined like this, you know, back in the lecture 11. So okay, so you make a category out of this, and you should be now asking a question from me about this. It seems to be incomplete, but Lin is not complaining, right? Exactly. I have not proved the axioms here. Yeah, I mean, so for example, when you prove something is a monoid, you have to prove associativity, and you did it already many times. So why is it that here I'm not putting these things, but it works? Because of this tactic, obviously, remember? So that obviously does these things for you for category theory. So that obviously was introduced here. And in the lecture last time, I said, I'm not going to talk about it. Now I'm talking about it. Right? It was here. So this dot obviously. You see, for these axioms here, I said dot obviously, which means now whenever you want to provide an instance, you are saved some word from something, some word. Okay. In the homework, you're not allowed to do this. So you have to actually not use obviously, because, okay. And obviously is a technique that not 100% of times works. So maybe it's better to not have those headaches. But let me do final example and then of categories, and then we will do not today, but next time, some functors between these categories. So here I have a monoid, right? I have a type which has a monoid structure, and I want to make it into a category. How do I do that? The idea is like, it will have only one object. So that's why I use unit type. So when you want to put like category structure on some type, so this is the type of your object. It's unit, it has only one object, okay? So the idea is this. I have a monoid. Right? So it has, if you have X and Y, you can multiply it. It's associated. Out of this, I want to make a category which has only single object. That's great, right? Single object. Okay, let's call this whatever. This is unit type. For the morphism, for any element of the monoid, I have one more from start to itself. And if I have another one, I would say that I compose Y with X to be Y times X. So that would be another morphism. And this is called the delooping of this monoid. Okay, so let's write it down in V. So, okay, already the object is unit type, which means it has only one object, unit, right? But what about the hum? So I have to say like lam X, lam Y, and what now? Okay, I have to give a type. So what is the type of this is essentially type of morphisms from X to Y. You see, X and Y are from unit type, which means they can be only one thing. They are at the start. Unit type has one thing. So it actually doesn't matter if you name it X and Y because they are just one thing. So just put underscore. So the type that you want to provide is the type of morphisms from that star to its star. M, right? So that's the whole monoid. Because I said every element of the monoid is going to be a morphism in there. So you just put M here. Okay. What about identity? What is the identity morphism like from star to a star? What do you think like identity morphism? So it has to come from an element of a monoid. Which element of monoid do you choose to be identity morphism? One, right? Why do you do that? You could have chosen other things, I guess. Not really. I mean, we know that. Yeah. Okay. So not really. Okay, but it turns out to be crucial. Let's see. What about composition? Well, I told you how to compose morphisms. It's just multiplication, right? So it's going to be. How do I write that? Well, there was a notation for it, so I just put like this. Oh, it doesn't work. Ah, okay. Yes. So lambda blank, and maybe put as many blanks as Lynn likes. Okay, it's happy now. So now I have to prove that composition of identity with any element, right? For any morphism F from X to Y. So those X, Ys are dummies because there's only one X and one Y in this category. There's only one object. But I have to say like composition of F with one, it's going to be F. But what is one? One is now the new unit element of monoid, like the neutral element. And composition is just multiplication of in the monoid. So this is really F times one, right? So, okay, we have, I guess, do some bunch of intros, blank, blank, blank. Are you happy now? Okay, yeah, it's happy. And now I have to do what? This is F times one equals to F. Or like has what was rewrite mul or like simp. Simp would work, but we can also give specific lemma which we are using, which was mul mon one mul. It finds it already for us. Okay, great. So now I'm going to copy all of this And there is very small change we have to do for the other side. Yeah. And for this, well, again, bunch of intros, but I think more than 1, 3. No? What's the code? Yeah, there's one more. There's, okay. Oh. Sim. And you could, I think, do sim already here. No. That's too much to ask. Okay. So later we will prove that if you deloop a monoid like this, and you deloop another monoid n, if you consider a functor between deloopings, would be just a monoid homomorphism. So if you have two monoids m and n, and if you have a monoid homomorphism, right, that would give rise to a functor between their deloopings. So that's quite interesting. Okay, James, I want to say goodbye to you. Do you have a question?
Not yet, but I'm sure I will after I guess looking deeper at this. It's
Okay, sorry, I can't hear you still, but
yeah.
yeah, you're good. Okay, thanks. See you next time.
All right.
Okay, your question. Let's move out of the room because I think I'm not going to.